This is chapter 8 in the older editions of TRO. This is chapter 9 in the 5th edition, or the new edition of TRO. It's all about the electron configuration. I think that's actually the title of it, Electron Configuration. So at the end of the last chapter, we saw that, the orbitals can be arranged by the type and which period they appear in. And the very last thing we were talking about was the magnetic effect and how it kind of affects the 3D energies, different than the 4 S's and the 3 P's. And so we ended up last slide with this electron configuration for the atom. So you want to learn this. You got to memorize it, and you can see that there's a pattern here. The first 2 electrons are 1s electrons. Then you have 2 of them is 2s, 6 of them is 2p, and then it repeats here. So 2s, 2p, you just change 2 for 3, and then it repeats 3s, 3p. Then when the 4s come in, and things change a little bit. So it's 3s, 3p, 3s2, 3p6, and here's 3d10 over here. But the 4s2 is lower in energy, so you lift that one first. And then you have 4s2, 3d10, 4p6, and here's 4d10 way over here. So you can see this is a repeat, 4, 3, 4. This is 5, 4, 5. And then you have this next set with the F orbitals. I'm not going to ask you about the F's, but maybe the cut should be right here for what you need to memorize. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on. You want to be able to just rattle that configuration off. All right, now there is a relationship between the electron configuration and the periodic table. And the quantum number, the principal quantum number is right here, 1, 2, 3, 4, 5, 6. So you can look at the number of electrons that one of the elements has, and you can find it on the periodic table. For example, sodium. So the last electron that fills for sodium, it's got 11 electrons. The last electron is going to be a 3. This is the S block right here, and it's in the first group. So it's going to be 3s1. And, after the next slide or two, you should be able to just look at sulfur, for example, and see that it is in the 1, 2, 3, 4th position in the P block right here. The pink is the P block. So this is the S block, the P block, D, and F. So if you have sulfur right here, then it's in period 3, and you can take the 6 here out of the 16, or the 6 in the 6A is going to be 6 electrons in the N equals 3 period. So you got 3s2 and then 3p4. So it's in the 4th position. The last electron that fills was going to be 3p4. Anyway, let's look at some examples and you'll see what I mean by that. Table, I just talked about it. So it's right here. Sodium, you start just by saying it's got 11 electrons. And that's what I was saying before, that 3s1 is the last electron that fills. So period 3, group 1, is the last electron that fills. Find it on the periodic table. So vanadium's right here. It's got 23 electrons, and this is the D block right here. The yellow is the D block. So 20. And chromium is right here, right next to vanadium. It would be exactly similar if there were not for an exception. With this period in the D block, there are 2 exceptions that I want you to know about. One of them is chromium, and the other one is copper. So we'll start by talking about chromium. So here's vanadium, and it's right here. So you can use this simplified, abbreviated notation referred to as the core configuration and then the valence electrons. So what you do is you take the electron configuration of the rare gas element that is right before it. So vanadium is 23, 22, 21, 20, 19, and 18. So you just keep working back until you get to this column, and whichever rare gas element it is, that'll be the core configuration of this one. So this one has a total of 18 electrons, and then the part that's left over would be 4s2 and 3d3. So what did I mean by all of that? It has the exact same, see, 18 electrons for argon, so it has the exact same configuration as argon. You will find it over here. It has 17, and notice, what were we just talking about with vanadium, right? The last 5 electrons, which are the valence electrons, are 4s2, 3d3. You see what these are right here? These are the valence electron configurations, given that the fact that there's an argon core. All right, anyway, so now we're interested in chlorine, actually chloride. So chloride is going to have a total of 18 electrons because it's got a negative charge, so it's got an extra electron. Find that in the periodic table. It's over here. So it's got a, it can form the 2+ ion. Is that what we're in? But if we just looked at calcium by itself, you could say, well, it's argon, and then it's, there's 2 more, so it would be 4s2. Or you could go through and say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So you could do it that way as well. So you look at the period and the position, and remember the different blocks and how the order of the electrons in the configuration. All right, so we got 20 for calcium. Let me go back and show you a couple more things about the periodic table, though. So chromium is one of the exceptions, and instead of it being 4s2, blow that up a little bit. So instead of this being 4s2, 3d4, it's 4s1, 3d5. Look down the group, you see the same thing for molybdenum, but you don't see it for tungsten, and this one's radioactive anyway. But so you only see it for the first 2 in the group and not for the last 2 in the group. Now copper, this is the other exception over here. Normally it would be 4s2, 3d9 because it's in the 9th position. 1, 2, 3, 4, 5, 6, 8, 9th position in the D block. But you have that promotion of one of the 4s's into 3d. But notice here that you've got copper, silver, and gold. They all do the same thing. So 5s1, 4d10, 6s1, 5d10. So that's what gold and silver are like. There's extra stability associated with this filled D subshell. Rule is that going down the group, any group, they're going to be getting larger. So even over here, the nonmetals, they're going to get larger. And then the other rule is that going across the period from left to right, they're getting smaller. Okay, so we can compare lithium and fluorine. I've got some examples for that. But they're getting smaller going across, and they're getting larger. They're getting smaller going up and across. They're getting larger going down and backwards, right to left. So we're comparing sodium to neon right here. Neon is in period 2, and sodium is in period 3. So right there, you can make the statement that sodium is larger than neon. First of all, neon is getting smaller going across. But even if you were comparing sodium and lithium, this one's going to be larger because it's got an electron in the next orbit. So let me show you that. Here, you're comparing aluminum to chlorine, and I have already told you they get smaller going across. So if we did the diagram, we have 13 and 17 for this one. Okay, so you have aluminum right here. There's 13 electrons, and look at that, you got the neon core, and then you have 3s2, 3p1. These are the valence electrons. So there's 3 valence electrons. 2 of them are in 2s, and 2 of them are in the 2s and 3s and 3p, sorry. So there's 13 electrons. Let's go back to for aluminum. So the first one we want to look at is sodium. And sodium, you go back to the pure. So sodium has 11 electrons, and you just want to fill them into the electron configuration. 1s2, 2s2, 2p6. And you're counting here. 2 plus 2 plus 6, that's 10. You got 1 more to go. And that's going to be 3s1. Now, again, you go back to the periodic table. All right, so then also you can look at the orbital diagram for sodium. And you need a new whiteboard for this one. Let me start all over again. You've got, all right then, so vanadium's an interesting one. And 3 electrons, okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Okay, I went through that pretty quick here. So you count in 23, you got 2, 4, 10, 12, 18, 20, 23. But you got to remember the order, that it's 3p6 and then it goes up to 4s and it goes back down to 3 again for the 3d. And let's see, let's go ahead and do the orbital diagram for this one, vanadium 23. Got the next one is chromium. Look at your periodic table again. 24 electrons. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. The problem here is that this is not correct. That's what you would come up with logically based on what we just did for vanadium. But instead, there is stability associated with the half-filled D shell. And so one of these s electrons hops over to the D subshell and fills it halfway. So this part is wrong. Instead, you have 4s1, 3d5. Okay. All right, so then if you wanted to draw out the orbital diagram for this one, is copper. So remember, there's 2 exceptions. If you look at the periodic table, copper has 29 electrons. So you have something similar here, 1s2, 2s2, 2p6, 3s2, 3p6, and then similarly, you're going to have a 4s1, and now you're going to have, instead of 3d9, you're going to have 3d10. And notice the 9 here if this were not an exception, there would be 9 in the D, in the 3D subshell. So this is an exception right here. So I want you to know these 2 exceptions. And also, let's see, I haven't talked about the core configuration yet. Let me do that. So let's go back to vanadium. That was copper. So these 2 are the exceptions, right? Remember those. And then now you have examples of an anion and a cation, and then just it's kind of fun to go back and look at vanadium 2+ when we're done with that. Okay, so then if you look in the periodic table for chlorine, so this has 18 electrons instead of the normal 17. It's got the extra electron because it's got a negative charge. 1s2, 2s2, 2p6, that's 10. 3s2, that's 12, and then 3p6 gives you 18. And notice that has the same configuration as argon. So the act of adding that extra electron to chlorine, which originally would have been 3p5, now it has the same configuration as argon, and so there is stability associated with adding the extra electron to form the negative ion, the chloride ion. All right, calcium is next, and that one, yeah, that's the 2+. And now you're going to take 2 away, right, to make the 2+ ion. So this is 18 electrons as well. It's the exact same configuration as chloride. So we also could say that these 2 have the core configuration of argon. All right, and then finally vanadium 2. I said earlier that vanadium has 23. If we're looking at vanadium 2, it's going to be 22 electrons. So the question is, are the 2 electrons that are going to be removed going to come out of the 4s2 or the 3d3? And the answer is they're going to come out of the 4s2. So the configuration for vanadium, it's 23 and it's lost 2. So it's going to be 21 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. Now you could write 4s0. Some people do that. I usually don't. And then it's going to be 3d3. Let's see if that works out. 10, 18, and 3 is 21. All right, so oftentimes this piece is just missing there. And that would be the configuration for the 2+ ion. Then the question is, what happens if you have vanadium 3+ with 20 electrons? So the question again is, for vanadium, are the 3 electrons going to come out of the 3d3, or 2 of them going to come out of the 4s and 1 come out of the 3d? The answer is the second one that I just described. So the configuration for this one's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, and 3d2. And again, 4s0 oftentimes is not even listed there. But in both cases, 2+ and the 3+, and that's the case for all these transition metal cations, that the electrons come out of the 4s2 first, or the 4s first, and then they come out of the 3d subshell. Okay, those are some good examples. You might be wondering what's the order, what is the organization, all of this, because I've shown you some exceptions, right? So these 2 are exceptions here. These are kind of strange because of the 4s2 losing the electrons before the 3ds. And then here's the example of the anion, and these are the examples for cations, but it doesn't get more complicated than that, especially since I'm not going to ask you for anything elements greater than 36. So I'm not bringing the d orbitals in because they tend to mix around and do their own thing. And sodium with 11 electrons, 1s2, 2s2, 2p6, 3s1. But then you have, so this is the electron configuration. And now you want the orbital diagram here. So you have 1s is the lowest. The next one up is 2s. Then we write the 2p's over to the right. A slightly higher energy, but basically we're just separating s's and p's. They're easier to see that way. And then it goes back to 3s. So you have Hund's rule. You need to think about, you need to utilize here. And this is the one that says that there's going to be 2 electrons per orbital. So first one has spin up, the second one has spin down, that's 2. Spin up, spin down, that's 4. Then Hund's rule says that if you're filling electrons into a subshell that has more than one orbital, then you're going to fill across first, and then you're going to come back. So you got 2, 4, 5, 6, 7, and then you come back 8, 9, 10, 11, like that. So that's the orbital diagram. And then you have the orbit diagram. This is based on the old Bohr model. The orbital is based on quantum mechanics. The orbit diagram has the nucleus in the middle. You have n equals 1 shell, n equals 2 shell, and n equals 3. Okay, so then you have, for n equals 1, there's 2 electrons. You look at the configuration, 1s2. For n equals 2, you have 2s and 2p, so there's a total of 8 in n equals 2. In the Bohr model, there's no difference in energy between 2s and 2p. They're all just the same. So 1, 2, 3, 4, 5, 6, 7, 8. And then for n equals 3, there's 1 electron. Put it anywhere you want. All right, so you get insight into sodium, how the electrons exist relative to the nucleus by looking at all 3 of these diagrams and the 2 diagrams and the electron configuration. You get insight by looking at all 3. So you want to keep all of them in mind. Now, if I say to you I want the orbital diagram, I do not want the orbit diagram. If I say I want the electron configuration, I don't want the orbital diagram. So you got to know the difference between them. Sometimes I want all 3, just depends, but know the names of these drawings, configuration, and so on. So then chromium, vanadium's an interesting. So you got 1s, 2s, 2p, 3s, 3p, 4s. Put the d's next over here. So you see I'm separating them. That's 3d. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, you get insight into where the electrons are. Without doing this diagram, you might not realize that vanadium has 3 unpaired electrons, right? And that has a result, a magnetic effect So you have 3 electrons there with spins pointing in the same direction. All right, and then if you're going to do the orbit diagram, so you got n equals 1, 2, 3. So you got 2 here, and then 8 here. That's a total of 10. 1, 2, 3, 4, 5, 6, 7, 8, like that. And then you have n equals 3, and there's a total of 2. 6 is 8, and then 3 more, so it's going to be 11 out there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that. This is the orbit diagram. And this is the orbital diagram. And the next part. So chromium has 24 electrons. You're going to have 1s, 2s, 2p, 3s, 3p, 4s, 1, 2, 3, 4, 5, 3d. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Alright, so you get the half-filled shell here, half-filled subshell, and this is, there's stability associated with that. Alright, then here. So vanadium is 23 electrons, and what we want to do, go back to the periodic table here. Let me write it out again. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So this part right here is 18 electrons, and this has the exact same configuration as, look at it again. So we're gonna call it that. We're gonna say that this is argon, and you put it in brackets. This is the core, and then the valence electrons are 4s2, 3d3. So the core electrons, the shells are filled. Subshells are filled, not completely because you have the 3D out here, but 18 electrons corresponds to a rare gas element. There's stability associated with that. The P shell, subshell is filled, the S subshell, and so on are filled. So then they're not involved in chemical reactions. This is the valence electrons here are the ones associated with chemical reactions. So that's why we separate them, because usually for chemistry, all we really care about are the valence electrons. So you would say vanadium, 23 electrons, and then an equal sign, or you'd write down configuration, something to that effect. Okay, so that's very useful. And students always say, well, which one do you want? And the answer is, depends what I'm asking. Lots of times I ask for the complete configuration, sometimes the core configuration. All right, so then where was it? All right, so elements in a group tend to have the same chemical behavior. So this is group 1A, starting with lithium, sodium, potassium, rubidium, cesium, francium. And the last electron that fills in lithium is 2s1. The last electron that fills in sodium is 3s1, 4s1, 5s1. So they all have the property of having one electron in the s, and that's why they all are going to become +1 when they become cations, when they become charged ions. And they're all going to want to react with halides because the halogens want the electron from the group 1A element. So you get similar reactivity for elements in the same group. Similarly here for the halogens, fluorine wants to become fluoride, so that this is a 6 here, and then you get this filled n equals 2 shell. And then here you have the same thing, it wants 1. Each one of these wants to fill the p subshell, and then it's the noble gas configuration again. And also here, when these last electrons are removed, then the cation is a noble gas configuration, and also the anion is a noble gas configuration. And there's reactivity also, similar reactivity associated with elements in group 7A. In this case, the elements become more reactive going up the group. These are for the anions, and over here the cations, it's more reactive going down the group. So here are the group 1A elements. Again, lithium, sodium, potassium, rubidium, cesium. Each one has one electron as the valence shell, and then the rest of it is a core of noble gas configuration. This is showing the radius, so it's getting larger going down the group, and the rest of this I'm not so worried. I wouldn't focus on that. The picture is what's so interesting on this one. So going down the group again, it's lithium, sodium, potassium. This is an example. You start here with lithium. It's going to react with water. You're going to get lithium hydroxide plus hydrogen gas plus heat. And the heat is, so the solution heats up. You've got bubbles there due to the hydrogen, the H2 being formed. Mild-mannered reaction here. Go down the group to sodium and do the exact same thing. Now you have sodium instead of lithium, and notice that there's some smoke and some flame, and also there's much more heat associated with this reaction, meaning that the sodium is way more reactive than the lithium. But what's interesting here is that there's so much heat produced that the hydrogen, the vapors above this, ignite. Okay, there's a spark associated with sodium dissolving in water, so there's a lot of energy given off for that, and it sparks the hydrogen gas and you get a flame. So it's quite vigorous. You go down the group one more time to potassium. Now this this stuff's flying around. You get pieces of potassium that are flying out of the beaker, and you really have to be careful with this one, but you can see it's way more reactive. You get a flame, and it's much hotter as well. So going down the group, the elements are more reactive if they are the metals. Here's a nice picture for the halogens or halogens, and let's see. I guess you can see also that you get the core configuration, and then each one has 7 electrons in the valence shell, and you can tell which valence shells they are. And then you can see it's getting bigger going down the group, so iodine is much larger than fluorine, and I would not worry about the rest of that. But it's interesting to look at this picture as well. So chlorine, which is higher in the table, is a gas. And it looks like it's got an equilibrium with a little bit of liquid here. It's hard to tell. At room temperature and 1 atmosphere, you would expect the entire chlorine sample to be in the gas phase. But bromine is next, and bromine actually does have liquid. It is a liquid, but under these conditions, it's also in equilibrium with its vapor. In the case of iodine, it's heavier, right? It's lower down the table. Now a solid can be formed, right? So it's a much larger atom. You have these stronger interaction between iodine atoms, or molecules actually. Each one is Cl2, Br2, and I2. But they're interacting more strongly due to their London forces, which we're going to study later. So that's why it's in the solid phase. But this is interesting as well because you have a solid in equilibrium with the vapor, and that is referred to as, I'm drawing a blank, sublimation. So that's a periodic trend, right? You start out with the gas phase over here, then you get liquid, and then finally get solid as going down the group. Where's the last one, right? Oops. Examples. All right, so then we want to talk about the radii and the trends with regard to the periodic table. In general, let's go back to the table here. The general. All right, so then first we want to compare the radii of sodium versus neon. Let's actually go back one more time. Okay, so you've got sodium, which has 11. So you got N equals 2. N equals 1 and N equals 2. There's 2 electrons here. Then there's 8 for N equals 2. 1, 2, 3, 4, 5, 6, 7, 8. And then there's one more out here. This is sodium. And then for neon, it has 10. And so you don't have this last electron in N equals 3. So you just get this. So that is neon. So you're going to say sodium is larger than neon because it's got an electron in N equals 3. Right? The next one is aluminum versus chlorine. So this way. The next one is sodium versus sodium plus. Versus chloride, yeah. Right here. So that covered all 4 examples there. So aluminum 13 versus chlorine, which is 17. Which one is larger? So let's see, the argument goes this way. Aluminum has got 13 protons in the center, and then the electrons are, there's a total of 13, so that would be 2, there's going to be 8, and this one that's 10, and then this is N equals 3 out here, so 2, 1, 2, 3, 4, 5, 6, 7, 8, and then there's 3 more, 1, 2, 3. Now chlorine has 17 protons in the middle, and the last electrons are also in N equals 3. So you get 2, 1, 2, 3, 4, 5, 6, 7, 8. So that's a total of 10. Now I get 7 more. 1, 2, 3, 4, 5, 6, 7, 8. All right, now they're supposed to be about the same size the way I drew them. There is this effect of going from left to right across the period. You'll see this contraction that takes place. So you consider the electrons that are in the outer orbit. This electron is attracted to 13 protons. This electron in the outer orb, the same orbit, right, is attracted to 17 protons. And so the attraction between the negative electron and the positive protons, the positive nucleus, is going to make this one smaller. This one's going to be larger. So aluminum is larger than chlorine for that reason. So the attraction to 13 protons is not as great as it is to 17 protons. Therefore, the contraction is going to be greater for chlorine and the atom will be smaller. All right, and then the next. I think it was chlorine. Okay. Covered all of them. Then if you look forward, so you have 11, sodium has 11 versus sodium plus, which has 10 electrons. You have these orbit diagrams work really well for these arguments. So you have 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. 1, 2, whoops. 2, 3, 4, 5, 6, 7, 8, 9, 10. So sodium neutral is larger than sodium plus. And in general, we could say that the neutral metal is larger than the cation, larger than its cation. Then the last one, so I think that here, so the last one is chlorine versus chloride. And chlorine has 17 electrons. You're going to add one more, so chloride has 18. And let's see, for 17, you got 2, 8, 10, so there's going to be 7 in that one. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8. 1 and 2, that's chlorine. Chloride has an extra electron. I'm going fast now. 2, 6, 8, 10. 1, 2, 3, 4, 5, 6, 7, 8. So what is the same between these two is that they're both chlorine, meaning there's 17 protons in each nucleus. So in this case, you're looking at the fact that the outer electrons are attracted to the nucleus. You're going to get the exact same effect here, so that's not the issue. The issue is that you have one more electron that is not balanced by an 18th proton. So this is what makes it the negative charge. But there's nothing to off-balance it. So it has the effect of kind of pushing out the other electrons in the shell. And it causes the whole shell to increase in size in order to accommodate it. And that's the reason why the chloride is going to be larger than chlorine. So in this case, you've got the general rule here that the neutral nonmetal is smaller than the anion. So you can use those rules. Those are hard and fast rules for element versus cation and anion. All right. Oops. There's a diagram. Well, there's this one. I was going to show you this one first. Let me do this diagram, which I like this diagram a lot. So you got a lot of things going on in it. This is the radii. And let me just write out make it a little bit smaller here. Okay. So period 2, the elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And in period 3, it's sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Try to line them up there. So this has to do with the radii as well, this diagram. And remember we said going across the period they're getting smaller. So this is an actual plot of the radii. So this is going to be lithium, boron. I meant to say beryllium on that one right there. This is beryllium. So it's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And the size is going down, going across the period from left to right. And then the next one is sodium at the top, which is the largest, getting smaller, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, like that. Now, in the next period, you've got 4s2, 3d10, and then 4p6. So these transition metals in here, they have their own weird behavior, as you can see, but there's also a contraction as well. So that's probably what you want to take home. Well, the other thing you can look at here is that going down the group. So this is going across, right? If you're going down the group, you got lithium, sodium, potassium, rubidium, and cesium. So the size is increasing going down the group, and the same thing for the end of the group. At the end of the period, you're going down the group again with the rare gases. You get the same effect. So the increase is going down the group. So that's a good one to look at first, then I'll come back to it. Over here, so this one is kind of nice. This is going to be group 1, 1A, and you're looking at the radius here. So the electron radius, which is half of the diameter. So the gray would be the neutral. You can see it's getting larger going down the group. So that you have the arrow here. It's getting large. The elements get larger. The cation is smaller. We just talked about that. And it's smaller than the neutral, but you have the same effect that it's getting larger going down the group. And then going across the period, you can see it here. It's getting smaller, so the neutral is getting smaller. The cation is getting smaller as well. So the size is increasing this way. When you go this way, they're getting smaller. Come back. And for the anions, it's similar. So you have the neutral. Nope, I got that wrong. The gray is the neutral. And here we say the anion is larger than the neutral. So the radius here is greater than the radius for that one. But you still have the effect that going down the group, they're getting larger. And also, if you had more elements, you'd see they're getting, not only is the neutral getting smaller going across, but the larger anion is doing the same thing. All right. That's my heater on its last leg. Gotta get a new heater. All right, then the last topic here is the ionization energy. And this is the energy needed to remove an electron from a neutral gaseous atom. So it's gas phase, it's neutral. You want to irradiate it with some kind of light or some kind of energy. And the question is, how much energy do you need to actually remove the electron and make sodium plus, and you have the electron. And I mentioned this when I was talking about the Rydberg equation before. And here it is. This is the Rydberg equation. And in terms of the energy levels, You have n equals 1, n equals 2, 3, 4, 5, 6, and so on. This is a simplification. Finally, you give it enough energy that it goes all the way to infinity. So how much energy does it take to get to infinity? Infinity just means that the electron is actually removed. So whatever that energy is, that's the topic. That's the ionization energy. So you can treat it like a Rydberg equation, and you can do quantum mechanical calculations, get the exact same result. But in the case of absorption, the equation is the same except you have a negative sign here. You do not have this for the emission that we studied earlier. That's just going to give you a positive number over here instead of negative, because the difference between these two is negative. So 1 over infinity is 0, same with 1 over infinity squared, so you have 0 minus, so in other words, the first state and then the last state, the initial and the final. And remember, it goes 1 over n final squared minus 1 over n initial squared. And you can do that. So this is just going to be equal to -1, and then multiply it times -1, you're going to get this, which is just the Rydberg constant. And then you can use, right here, you're looking at the energy, so it's energy is equal to h nu. That's the Einstein equation. And then you're going to use C is lambda times nu. Solve for nu right there. So write it again, E equals h nu. And nu is equal to C over lambda. And substitute that. So you're going to get E is equal to hc over lambda, which is this right here. So you've got 1 over lambda. So in other words, this is hc times 1 over lambda. So you just take your 1 over lambda here and multiply it times hc, and then you have energy. Now when you do that, you're going to get joules. And people who study ionization energies prefer electron volts rather than joules. And there's a conversion factor that you don't have to worry about to go from one to the other. So I would not worry about that. But you can calculate this. And when you look at these energy diagrams, that one I showed you from the last chapter with all the details of the transitions, you'll note that the energies are in terms of electron volts. Oftentimes it's EV like that for electron volt. All right, so anyway, that's the concept there for ionization. We use units of energy. And then it turns out that if the electron is closer to the nucleus, you got a negative and a positive, right? If it's closer to the nucleus, then it's harder to remove the electron. So the closer it is to the nucleus, the harder it is to ionize it. And that's a rule that you can use to figure out what the trends are for ionization energy. All right, so this is the ionization energy graph, and it's similar yet different to the size, the radii. Instead of starting with lithium at the top and going down to neon, now you have lithium at the bottom and going up to neon. So remember, neon, this is going across the period. This is smaller, this is larger, right? It's decreasing in size going this way. So the smaller it is, the harder it is to pull the electron off it. Therefore, it takes more ionization energy, more energy to remove an electron from neon than anything before it in the same period. And you see the same trends. So the smaller ones are at the top now, but you still get the effect that going down the group for the rare gases, the ionization energy is less, meaning that the small is right because xenon's larger. So coming up the group, helium is the smallest. That's the one that's hardest to ionize because it's very small. So you can think about that relationship to the size. The last slide here is showing that not only can you pull off one electron from each one of the elements here, and this is the energy that it takes to do that, but you can actually pull off a second electron, third electron, fourth electron, 4 and 5. I don't know why they're switched, but I never realized that until right now. But if you look at aluminum here, that's kind of interesting. So aluminum let's go back and look at the periodic table for aluminum. So aluminum has 13 electrons, 1 s2, 2 s2, 2 p6, 3 s2, 3 p1. So that's the core right there. So now to pull the first electron off, it takes 578 kilojoules. That's this one right here. Out it goes. Then you have to break this pair, right? There's stability associated when you have spin up, spin down. The orbital has 2 electrons in it. So it's going to take way more energy, 1820, to pull that second electron out compared to the first one. And so then it says the first one goes here. You got one more left. Look at it, it's way more energy for that. But that's nothing compared to once you've taken all of these electrons off, now you're going to pull an electron out of the stable core, right? And look at it's 11,600. It takes a ton of energy to try and break up that stable filled subshell, which is part of the core. So if you wanted to, study and learn anything about this graph, probably focus on aluminum here. I think that's probably one of the interesting ones. All right, so that is the chapter, which in the new book is chapter 9. We're ready to start to talk about Lewis dots in the next chapter, covalent bonding, and that'll be coming up next. Thank you.